So this is our paper, Learning to Rasterize Differentiably. During the first half, I will talk about some background on our proposed method, and then Papa will share the results with you. So let's start. In traditional rasterizer, also known as hard rasterizer, we sample a point on the plane of triangle for each pixel. If the point is outside the triangle, we set the visibility of the triangle to 0. But if the point is inside, the visibility will be 1. In this way, the rendered triangles will have hard edges. The problem with that is when the triangle is moving, there will be a sudden change of visibility near the edges, at the pixels near the edge, which introduces discontinuity. But the question, and for the depths also, for overlapping triangles, we set the visibility of the triangle that's closest to the camera to 1, and the other triangles will have the 0 visibility. So this time we will have hard occlusion. And so the change of depth will also cause sudden change of visibility. So the question is, why do we even need differentiable rasterizers? In many applications like shape reconstruction and pose estimation, we need to build an end-to-end optimization model. So usually we have some parameters and we pass them to the rasterizer to get our final image. And if you have a reference image and compare this image with the rendered image, we can get a loss and backpropagate it to update the original parameters. So the process of backpropagation is necessary. That's why the rasterizer has to be differentiable, which currently is not. A way to make the rasterizer differentiable is by enabling auto-differentiation. So instead of sampling just one point per pixel, we can sample multiple points based on a Gaussian distribution. In this way, when the triangle is moving, the visibility of a pixel will change continuously and gradually. So, and it will also be based on the Euclidean distance from the edge of the closest triangle. So we will have the cumulative distance function of Gaussian distribution, and the triangles will have soft edges. In this case, also for the occlusion part, the visibility of the triangle will be determined continuously based on their depth and their closeness to the camera. So the closer a triangle is to the camera, it will have higher probability of being visible. In previous work, GenDR, they analyzed various distributions with different CDFs. And for each CDF, they grid search the optimal value of softness. So, sorry about that. For example, in the logistic distribution, the change of the sigma variable defines the shape of our CDF. So when the sigma is closer to 0, we will have a value similar, the CDF function will be close to a step function, and when the value of sigma gets to infinity, we will have a plateau function. The problem with this is that the sigma variable should be grid searched, and so we should find it manually. In our MLP, we want to take this a step further. Why should we find the optimal CDF function and its softness manually? We want to propose an MLP to parameterize this softening operation. So with MLP, we can basically approximate any arbitrary CDF in the whole continuous space of CDF functions. And essentially, MLP is learning the sample distribution, but in practice, we analytically compute the visibility of the mapping distance. And the way that we train our MLP is that take a task of 3D reconstruction as an example. You have some vertices that have to be changed to match a reference image. And we also have the MLP. We first render the image with the vertices using our MLP. and compare it to the reference image. By getting the loss, we can update the vertices in a task loop. So the rendering image will match the reference image at the end of the task loop. But what about the MLP? To update the MLP, we will backpropagate the losses in another meta loop that will change the shape of MLP. So in each iteration of meta loop, a new instance of task loop will be run. Another good point about the meta learning is that it can be run in parallel. So you can have 120 different angles for a camera and do the optimization all at the same time. So this concludes the introduction part. I will pass it to Chanka for the results. Thank you.
Thank you, Hamida. And to evaluate our method, we have several types of tasks in our experiment. First, we design a 2D shape reconstruction where we randomly initialize hundreds of triangles and to match a reference logo. We compare our MLP with 4 other CDFs from previous work, which are the generally best performers according to their experiment. And in the second row, we show the image error, which is the difference between reference and optimized result. We can see using MLP can get the least image error. An advantage of MLP is the transferability. We design a transfer task and we initialize thousands of triangles to match a more complex reference. But in this task, we still use the same MLP learned from the last task, and it still gets the best result, while the other 4 CDFs are research for this specific task. And we add one more dimension to optimize the 3D shape. In this task, we initialize a sphere object to match a silhouette of another object at a certain view. And we can see from the second row, our MLP can get the closest fit and the least image error. Again, we transfer this MLP to a new object, and it still gets the best result. The 2 tasks above, in the 2 tasks above, we find the best of softness and set it fixed during the whole optimization. But there are some more flexible strategy can be used in the optimization. For example, previous work decide a decaying softness scheme in the camera pose estimation. So they will decay the softness from a large value to a small value. But for MLP, it's difficult to find a precise parameter set to get large or small softness, but we can directly update the parameter of MLP with gradients along with the optimization. And we can see using MLP can get to the global optima very soon and stably, while the others will end up to be terrible. That's because the MLP, once the MLP find the best softness, it will just stay there and it won't be updated anymore. But for manually decaying strategy from previous work, it's difficult to find when and where to stop the decaying. And apart from softening the edges, we also test our MLP on softening the depths. We design a task to optimize the order of several overlapping faces. And previous work used softmax on the depths, and they also have a scale, a sigma to control the softness. But essentially, it's applying exponential function on each steps and normalize them. So similarly, we can replace the exponential with other CDFs or the MLP to soften the depths. And in this class, we will see only using MLP can get a correct order relationship between these bases. And to validate that each type of task has unique optimal softness, we did a cross evaluation. So in this experiment, we applied the softness learned from each task on the others, and we can see the smallest error are on the diagonal, which means each task has specific optimal softness, and it can not be generalized to across different types of tasks. And we also evaluate the time performance of our method, and we can see using MLP will cost more time on the training than researching CDF. But actually, in an inverse application, we usually cannot know which CDF is the best choice. So we might probably need to search across multiple, like dozens of CDFs, and it will cost more time in total. And the MLP can get the best result in this tree-shape optimization, because there is a probability when you traverse dozens of CDFs, none of them can get better than the MLP, and MLP can at least perform the same as CDF. And for other tasks, the situation is similar because in our experiment, we tested out the minimal workable MLP with only 5 layers and 56 parameters. So the actual computations are analyzable, which is less than 1% of the whole computational graph. In conclusion, we parameterize the soften operations, and we use meta-learning structure to learn from the continuous space. And we also explore the transferability of the meta-learned MLP, and which shows the potential to be generalized to more complex tasks. And we also studied the dynamic softness strategy during the optimization, which shows the ability of MLP to adapt a specific task instance. In the future, we plan to extend the same idea to more complex applications, like those with complex materials and light settings, which also introduce discontinuities. And we can also explore meta-learning the softness for each step in the optimization, because dynamically update the softness will also add extra computations. And we can also study multiple task optimization, like we can combine different softness for different tasks, or we can find a global softness for all of them. And it will be more helpful for realistic inverse problems. I would thank you for your listening.